Hey, my name's Thomas, and this is a talk recording for the Formal Methods in Computer-Aided Design Conference 2020. I'm going to talk about a novel thread-modular abstraction for proving safety of parameterized programs, and this is joint work with Georg Weißenbacher and Florian Zuleger at the Technical University of Vienna, Austria. This talk is structured in 4 sections. We will first look at what are parameterized programs. Then we will look at why safety checking them is really challenging. In the third and main part, I will try to convince you that things can be made a lot easier than we thought so far. And then we will look at some evidence that this actually works in the form of experiments. So what are parameterized programs? And the program part of this is just our usual notion of an infinite state program. The parameterization means that we look at an unbounded number, n, of threads that concurrently execute this infinite state program template. Let's look at an example. So we have this program template here that first increments t and then increments s, and t and s are both shared variables. And then this induces a parameterized program that looks like this, where we have n threads all executing the same identical program template. And then the safety verification part of this means that starting from some set of initial program states, in our case where t equals s, we want to check some safety property. For example, this assertion here that says t is always greater than s, and their difference is no more than the number of threads in the system. And now we want to check this property for all runs of the system, but also for all system sizes. So a verification problem becomes quantified over this additional parameter, n. Now let's look at what makes verifying parameterized programs tricky. And the challenge here is really that we have 2 dimensions of infinity in our state space. The first dimension is along the parameter, because the parameterized program induces an infinite family of systems that we all have to check. So to prove that this property holds in our system, we actually have to check a system of size 1, a system of size 2, and a system of size 3, and so on. And this gives us this first dimension of infinity along the parameter n. And then for each of those systems, if we look at them, we find that they themselves are an infinite state program where variables range over infinite data domains. And this gives us the second dimension of infinity. And when we look at state-of-the-art methods for proving safety of parameterized programs, we find that they all introduce really heavy proof machinery. And this is because they kind of mix together these 2 dimensions of infinity. In particular, they all introduce very complicated, specialized new abstractions, new program models, and intricate new automata theory. And this raises a lot of questions. For example, if we have some new notion of program model, then how do we model common verification problems? And it turns out that we might not even be able to do this with these state-of-the-art methods. If you have specialized abstractions, but how do we refine them? How do we find good heuristics for refining them? And then overall, how do we do efficient implementation of these novel techniques? All of this makes verifying safety for parameterized programs really tricky. But what we want to focus on in this talk is that it might not be as tricky as we thought. Because when we looked at the state of the art, we thought, well, can we do something different? Can we, instead of introducing all of these new notions and heavy proof machinery, Can we maybe just use well-known methods instead? And it turns out that we can. And in this work, we introduce something that we call thread-modular counter abstraction. So let me show you an overview of our abstraction framework. So we start out with this two-dimensional parameterized program verification problem. And then what we do is we apply something that we call thread-modular counter abstraction, or for short TMCA, to this two-dimensional problem to fold one of the infinity dimensions, the parameterization, into the other one. And this gives us a TMCA model that is just infinite in one dimension, the data domain. And this, of course, is just an infinite state program that we know how to model check. So we can just apply an off-the-shelf software model checker, for example, using predicate abstraction, that turns our verification problem into just a classical finite state model checking problem. And the contributions of this work are really along these two abstraction steps. So we have contribution 1, which introduces TMCA, which is a novel combination of something very similar to counter abstraction adapted to software, combined with thread-modular reasoning. And then in the second abstraction step, although we could use off-the-shelf model checkers, we saw that they diverge on our TMCA models. So what we do here as a second contribution is introduce a new predicate selection heuristic that allows software model checkers to converge on our TMCA models. So in a nutshell, what we present here is a clean two-step abstraction framework. Clean because it treats each of the dimensions of infinity separately. And remember that this was a problem with all the previous work, which kind of jumbles them together. Also, we do not introduce any new heavy proof machinery. Instead, we build all of this from a combination of well understood existing methods. So let's look at the first step in our abstraction framework. And the main idea here is really to express the unboundedly replicated local state, the parameterization, in something that's already infinite, our infinite data domain. Let's look at this on our example. And to introduce some definitions, we will refer to this first thread that has the assertion on it as the reference thread, and to all of the other threads as the environment. And now TMCA is split into two steps. And let's look at the first one of these, which is an instrumentation phase. So what we will do is we will introduce auxiliary counter variables, one for each program location. So note that our program here has 3 program locations, L0, L1, and L2. And what we will do is we will introduce one counter per program location such that the value of this counter equals the number of environment threads at that particular location. So as an example, if we look at the first transition of the first environment thread, which is the T++ transition, it will change into something like this, where we first assume that there is at least one thread in program location 0, and it has to be if this thread is able to take this transition. Then we just execute the original statement T++, and then because a thread just changed location from L0 to L1, we have to adjust counters psi0 and psi1 accordingly by decrementing the number of threads in location 0 and incrementing the number of threads in location 1. And then we do a similar thing for the second transition here. We assume that there is at least one thread in location 1. We execute the original statement S++, and then again, we adjust counters because one thread just switched from location 1 to location 2. And we continue this instrumentation identically for all of the remaining environment threads. The second thing that we have to do for instrumentation is we have to account for these additional auxiliary variables in our initial program state. And what we're going to do for this is we will assign the number of threads in location 0 to n-1 because we have as many environment threads. And then because initially no thread is residing in any other location, we assign 0 to all of the other counters. And this is the first step of TMCA, instrumentation. Now let's go on to the second step, in which we will build a thread-modular abstraction to go from n threads to just 2. And what we do for this is we first just duplicate the reference thread. We will keep it as is. But then we will build a thread-modular summary of all of the remaining environment threads. And how we do this is just the usual thread-modular abstraction. We project away all local state. In our case, this just means control locations. The program counter of each of these threads gets abstracted away, which results in something that has no control state, or just this one control location, and all the transitions of these n-1 threads collapse into just 2 transitions in this summary. Now, note that because of the instrumentation that we did up front, the summary still retains some of the flavors of local control state that we saw in the original program. In particular, we can only execute these 2 transitions in a specific order, and we can only execute them a specific number of times. And this is what this first instrumentation step gives us. So now we have abstracted this system, this instrumented program with n threads into something that has only 2 threads. And then we know what to do with this, right? We can just do our usual interleaving construction. We just build the cross product of each of these and end up with something that looks like this. And now this is perfect. It's just a sequential program. It's something we know how to model check. We just use an off-the-shelf software verifier. And this is the first step and the first contribution of this work. And what we did here, just to recall, is to express the unboundedly replicated local state in the already infinite data domain. So let's zoom out again and look at the whole verification pipeline, and now focus on the second step, where we do predicate abstraction to model check our TMCA abstracted model. Let's go back to our example. Now this was perfect, right? It was just a sequential program. We know how to model check. But unfortunately, it has kind of uncommon structure. It comes with these many self loops, and this is nothing any software engineer would ever write. And there's some folk wisdom in predicate abstraction, which is you should never refer to loop counters, because that leads to tracking the variables of those loop counters and just useless unrollings of the loops and divergence of the Siegel loop. Now the problem here is, in our abstract model, everything's a loop counter. What should we use as refinement predicates? And it actually turns out that a bunch of software model checkers that we tried all diverge on these abstract models. So for example, we tried the model checker ELDWICA, and it finds the following refinement predicates. It first finds 2 is less or equal than t minus s. This kind of rules out a spurious counterexample where each of these environment transitions is executed once. But if we use this refinement predicate to rule out the spurious counterexample, it finds another one, and this is ruled out by predicate 3 is less or equal than t minus s. And this rules out a longer spurious counter example, but it's again just loop unrolling, and it keeps doing and finding predicates like this with ever increasing constants, but it does not converge. And we saw similar behavior with the spacer horn clause engine in C3. So what we introduced in the paper is a novel predicate selection heuristic that finds refinement predicates that look like this. T minus S equals the number of threads in location 1 plus 1. And together with the fact that our counters are never negative, this implies that T minus S is positive, which is just and proves the lower bound on our assertion. Okay, so this was the second step, predicate abstraction. So let's zoom out again and look at the whole verification pipeline. And again, let me emphasize that this is all built from well-known methods. We use counter abstraction or something like counter abstraction that we have adapted to software. We use thread-modular reasoning, and we use predicate abstraction. There's no additional heavy proof machinery that is specific to parameterized programs in this framework. So hopefully I have convinced you that this is not as tricky as some of the previous approaches. And now let's look at some evidence that this really works in practice. So we will look at a bunch of experiments. All the numbers I'm going to show are in seconds. And for experiments, we looked at 3 sets of benchmarks. The first set is our own benchmarks. Then we look at benchmarks taken from the software verification competition. And let me point out that in the past 3 editions of SVComp, no sound verification tool proved these benchmarks correct. And then we look at the third benchmark set that is taken from a paper by Ganjay and others. And we will look at 3 different categories of comparison here. We first compare to some state-of-the-art tools. Then we have our own abstraction, TMCA, but combined with an off-the-shelf model checker. And then we have our full verification pipeline where we do first TMCA and then our custom predicate selection heuristic. Okay, so let's dive in. The first third-party tool that we're comparing to is a tool called Pacman from the same paper as the third benchmark set. Now, unfortunately, we were unable to get this tool to run and to reproduce the results. So we are limited to citing results from the paper, and we couldn't try it on any of our extended benchmarks here. Then the second verifier we looked at is ELDWICA, which supports a parametric encoding. And unfortunately, it doesn't handle the last 2 benchmarks because they use dynamic thread creation. But it also times out on all of the other benchmarks. And timeout here is a timeout of 15 minutes. And this inspired us to get started with TMCA. So we first implemented just TMCA and used an off-the-shelf model checker, in this case, the horn clause engine in C3, to verify these benchmarks. And now, again, the last benchmark, maximum, does not have a thread-modular proof. That's our method. TMCA does not apply. Of the other benchmarks, it does really well on the first 2, but again, times out after 15 minutes on all of the others. And what we saw is what I explained earlier with the refinement predicate. So it was really just unrolling loops and diverging. So we thought, what if we use a model checker that has a bit more refined way of dealing with interpolation queries and refinement predicates? And we chose to combine TMCA with the off-the-shelf model checker ELDWICA, this time applied to the already TMCA abstracted program. And we see that this works better, but again, ELDWICA still times out on 5 of the benchmarks we have here. And this inspired us because it's always, again, due to loop unrollings, due to picking bad refinement predicates to roll our own predicate refinement heuristic. And this here solves also the 5 remaining benchmarks. It's the only approach that we compare to that solves these 5 benchmarks, which are highlighted in bold. And this really shows that we need both contributions of this work to solve parameterized program safety. So let me bring back this overview slide just to conclude. We saw thread-modular counter abstraction, a 2-step abstraction framework for proving parameterized program safety. We dove into these 2 contributions, TMCA, which is a novel combination of counter abstraction and thread-modular reasoning, and then our own custom predicate selection heuristic for TMCA abstracted models. Our implementation is available online on GitHub, and if you have any questions, feel free to drop me an email. Thank you very much.